She handles a lot of the grants and contracts, a lot of the budgeting and miscellaneous items. Lola Carter's our receptionist. She helped put this together and helped out with the food and arrangements. Andre Lewis is our cameraman, as well as other things. And you probably know him from Europe, working with undergraduate students, and he does miscellaneous things as well.
Andre's a jack of all trades.
Yes, in our office we have to be a jack of all trades, and you're always welcome to come here for information and for service. It's a great pleasure to introduce Rajib Ganguly, who is an assistant professor of physics and astronomy here.
Right, I guess officially physics, but
yeah,
subtext.
Yeah, and astronomy, they go together. One of the things that we wish to do with this program is to highlight our faculty, because we have a lot of brilliant scholars on campus, and so much of the time we don't get to hear about them. So in my office, this gives us an opportunity to share with you research projects that our faculty are engaged with. Often they'll maybe go off campus or go to conferences or academic conferences where they will give presentations like this. So it's kind of helpful for our faculty maybe to share with you a presentation before they go do that sort of thing. Dr. Ganguly's background is that he got his doctoral degree at Penn State, so he has spent time in Pennsylvania. He's also worked at the Hubble Science Institute, and he can maybe tell us a little bit more about that, which is located at Johns Hopkins in Baltimore, Maryland. And I found that to be very interesting, of course. So he has spent time there. He was he was also an assistant professor, I believe, in Wyoming.
Postdoc.
Oh, postdoc in Wyoming. So he moved here from Wyoming to the great state of Michigan. And recently he's had 3 grants from NASA. And so that's one of the things that we wanted to promote is his research with NASA. And of course those grants are competitive. So it's wonderful to have him here to share his research and scholarship with you. So I'm going to turn it over to Rajib. Also, he has shared with me that during his presentation, he is open for questions and answers. Sometimes we have speakers who prefer questions at the end, although he said you can wait until the end. And I'm just stalling for one more second because I have a distinguished professor coming in. His name is Dr. Robin Widgery, who retired from UM-Flint. He also taught at a number of years at Kettering when it was GMI. He saw this, that we were going to have this presentation, so he thought he'd come in and join us. So you have someone who's a fellow astronomer, although his field was more into business and communications. So he wanted to come in and see this. So it's wonderful to have him here. So I'm just kind of waiting for him to grab his snack. Dr. Widgery, do you need a drink there?
No, I can walk on water here.
Okay. Yes. As you come in, I just wanted you to meet Dr. Ganguly, and then I'll turn it over to him to get started. Since you're a distinguished professor coming in.
I'm not very distinguished. I sometimes feel extinguished.
Yeah, I know. Hey, all right. As you can tell, he's got a great sense of humor. Where would be a good place? Where would you like to sit? Go ahead and. So, Rajib, I wanted you to be able to meet Dr. Widgery, Robin Widgery.
Hi, how are you? I've been studying black holes for a long time, for years and years.
All right. Okay, well, fantastic.
I can't say no.
So let's please go ahead and get started here, and please with your presentation.
Well, thanks, Terry. That was very kind. So my general research is in understanding how the biggest black holes in the universe form how they grow, how that relates to their environments. So I was thinking about doing this talk. I wanted to sort of tell it in terms of a sort of a story, be more narrative. And of course, every story has a cast of characters. So I thought I'd start off by acknowledging, maybe, if I can turn this on, acknowledging the cast of characters. These are all the giants whose shoulders I stand on. I will highlight the ones in blue. These are students here at University of Michigan Flint. I will embarrass this one right now, because she's sitting in the back of the room, Shonda Townsend. Shonda is going to be giving a talk on Friday morning, French Hall, room 5. You don't remember? You better find out what room, young lady. I invite you all to come see her presentation as well, because she's going to be doing more of telling you the story of how black holes form and how they evolve, and sort of the processes that involve. So, as a story, I thought I'd break this up into like a 3-act play, as it were. In the first act, I thought I'd start really general and talk about just black holes. Give ourselves a primer on what is and is not a black hole. Because we have some misconceptions that are perpetrated by certain industries in Southern California. And then talk about how they form, how those things form. And that'll set up sort of the conundrum that we're faced with it in my research, which is we have things that form that are much too large. And then we'll set the stage a little bit more in terms of providing a context for understanding how those things form and why we are interested in that. And then talk about more about some of the specific details. Not too many details, but some, enough to last us. And then we'll probably have a rather anticlimactic epilogue. Or I'll run out of time completely. Depends on what we do. Okay? And I encourage you guys to please ask questions anytime you have. I know Phil always asks questions. Phil was in my Astronomy 135 class. I told him I wouldn't embarrass him. I just did. All right, so a primer on black holes. What is and is not a black hole in the first place? A very simple operational definition for a black hole is any region of space where gravity is so unbelievably large that the escape velocity is larger than the speed of light. Light does not escape, hence we can't see it. So to us, it looks black. Sort of an artist view of what that might look like is this, where we look out in space and we see stars, and maybe there's this region here that's completely dark. No light is coming from that region of space. Because there's something there attracting the light. Light cannot escape. Let me talk a little bit more about what escape velocity is, since we're using this for our operational definition. Escape velocity depends on two things: the mass of the thing that you're trying to escape from, and how far you are from it. To put it in context, when we send rocket ships out into space, like with the Apollo missions and the shuttle missions, they all have to achieve a certain velocity in order to get up into orbit. So from the surface of the Earth, standing on Earth, Earth has a certain mass, and we're a certain distance away from its center. The escape velocity from Earth, from the surface, is about 25,200 miles per hour. On the other hand, to put it in further context, the astronauts aboard the International Space Station, they're farther from the center of the Earth. The Earth's mass doesn't change, but you are farther, and so the escape velocity is a little smaller. Not much, but it is smaller. It's only about 24,300 miles per hour. So I'm going to do the calculation here. On the other hand, what if we were somehow standing on the surface of the sun without burning our feet or the rest of our body, getting a really good suntan? Well, the sun is large, it's about 100 times larger than the Earth, but it's a heck of a lot more massive. On a factor of a million. My wife will check me on those numbers, fact checking. Putting those two things together, the escape velocity standing on the surface of the sun is about 1.4 million miles per hour. Much larger than either of those escape velocities. What if we did an experiment? Thought experiment. Let's take the entire sun and let's compress it to the size of the great state of Michigan. A couple years ago. If we compress it, that means we can be closer to the center. The mass of the sun stays the same. We're closer to the center. The escape velocity goes up. In this case, if the sun were the size of Michigan, the escape velocity will go up to about 43 million miles per hour. These are large numbers, not as large as what economists use these days, but large still. What if we went even farther and shrunk it down to the size of Longway Planetarium that's down the street on Pearson? Longway Planetarium, the dome is about 50 feet in diameter. So something that large, if we were standing on the surface of that object, the escape velocity will be 30 billion miles per hour. So there's a factor of 1,000 going from here to here. That's a million, that's a billion. Well, here we run into a problem, which is that the speed of light is a paltry 670 million miles per hour. There's a million. Which is about a factor of 5 smaller, 5? Check 5, maybe 50, smaller than this number. So if we had the sun, all the mass of the sun would be compressed to the size of Longway Planetarium. Gravity is so strong that light can't escape. Let's see this in a picture. So here's our wonderful city of Flint. Longway Planetarium is there at that red dot. We are over here. There's about French Hall. Here's our university here. The escape velocity, standing right there, is about 30 billion miles per hour. As we go farther from Longway, the escape velocity is going to decrease because we're farther from that object. At some point, at some distance, the escape velocity will be equal to the speed of light. And that's given by this ruler here, which is supposed to be showing us about 3 kilometers. So the escape velocity from this object out of 3 kilometers from the object is about the speed of light. Anything inside that, light will not escape. Unfortunately, that includes our university. Other bad things happen when we are actually inside a black hole. That's not the subject of this talk. That hopefully gives us a little bit of context. There's this boundary here between where the escape velocity is larger than the speed of light and where the escape velocity is smaller than the speed of light. That boundary is called the event horizon. Usually when we talk about black holes, we're usually talking about how big is that event horizon. Plus, how much mass went into that small, really compact object in the sun. Those are sort of the two features. And those two sort of go hand in hand. The more mass something has, the larger its event horizon. And for something with the mass of the sun, that event horizon is about 3 kilometers.
It's about what?
About 3 kilometers. For me, it's about the size of the proton. Fortunately, I pale in mass compared to the sun, although I'm working on it. So, one of the myths that's perpetrated by our fine friends in Southern California, not to mention any names, is that black holes act as these giant vacuum cleaners in space. So they go around, they suck everything in, anything that they can get their hands on, and even then some. This is not true. It's actually very hard to feed a black hole. Black holes, do I want to do the baby analogy? Maybe I'll do the baby analogy, all right. She likes the baby analogy. Feeding black holes is like feeding babies. Okay? It's very hard, especially toddlers. Toddlers run around. If they don't want to eat, they're not going to eat. You follow them around. I was especially like this when I was a baby. Okay. But when you're feeding a baby that's hungry, they'll eat and eat and eat and eat. Of course, there's a limit to how fast you can feed a baby. And at some point, they start spitting back up. We'll get to that part of the analogy later. But just to come back to this. If we did replace the sun magically with a black hole that had the same mass as the sun, us out here, the orbit of Earth will be just fine. Earth would not magically be sucked into this black hole. Gravity behaves the same way. Nothing is different about that. Now, we probably would not be okay because we wouldn't have any light anymore. We wouldn't have any heat. We would freeze to death. But Earth would be just fine. We'd have to be within about 10 kilometers of this before gravity really starts behaving strangely, and we would actually be in danger of falling in. That's about 3 times the size of the event horizon. So I just talked about that this morning. So that's the stage for this part. How do we form? So we're not going to magically, spontaneously wave our magic wands and turn the sun into a black hole. How does that actually happen? How do you form these black holes? Can we get the lights? Can we turn down the lights, maybe?
This one or over there?
Oh, let's maybe the first one. Yeah, there we go. We can see that a little better. So this is a little montage that some friends of mine in Boston put together. This whole thing is actually a very large poster, which I just took and put in my presentation here. This is showing sort of the life cycles of different kinds of stars. And the stars are sort of ordered in terms of mass, with the smallest ones being down here, and the largest ones being up here. The sun is down here. This is a sun-like star. It's very nice and yellow. The life story of the sun is that it's currently fusing hydrogen into helium in its core, and eventually the hydrogen will run out until it'll have a helium core. The sun itself is massive enough that it can get hot enough to actually fuse helium into heavier elements like carbon and oxygen. It is not heavy enough, massive enough, to get hot enough in its core to fuse that carbon and oxygen into anything else. So what will happen, what we think will happen, is that after that helium fusing stage, the sun will eventually become this cinder, which we call a white dwarf. It'll become this little cinder that's sort of held up by the same kind of pressure that holds us up on the surface of the Earth. It's a certain kind of pressure, which Phil knows about because we talked about math in class. The more massive a star is, the hotter it's capable of getting in its core. And so the most massive stars up here are capable of fusing helium into carbon and oxygen, and carbon and oxygen into heavier things like silicon, and silicon into heavier things like nickel and iron. A funny thing happens. When they try to fuse iron into heavier elements, which is fusing iron does not release energy. And they want to release energy in order to support themselves against all that mass, all that gravity. Without having that sort of support system, fusing iron removes energy. So all of a sudden, when these guys up here try to fuse iron, they don't have a support structure against gravity. So the cores of those stars collapse. And they collapse suddenly. In this collapse, the core will collapse, but the outer envelopes of the star will also collapse, but then they'll bounce off the core. And that bounce is what we ultimately see as an explosion in a supernova. What's left behind is this very compact core that had a lot of mass, and so that's where we might get black holes, at least small ones. How big do they get? Well, the most massive stars that we've seen so far are a few hundred times the mass of our own sun. These stars, when they become black holes, they will give us black holes that are probably on the order of 80 to 130 times the mass of our sun, maybe even smaller, since it's only the core. Those masses pale in comparison to what my research is about, and that's sensitization. The biggest black holes in the universe. We have a conundrum because we observe black holes that are far more massive than just 80 to 100 times the mass of the sun. Let me give you a little tour here. So this is the sky. Now I could ask Phil what time of year this was, but I won't. You'll have to do that on the final exam. This is the constellation of Virgo, the Virgin, and this is Coma Berenices, Berenice's hair. I'm going to zoom in on this little region of space right here, highlighted by the orange circle. Those of you who have really, really good eyes, you might be able to see a smudge right there and right there. If I zoom in, the one smudge was those two things put together, and the other one was this guy. This is a galaxy, an entire galaxy, a collection of stars and gas. This is another one, and another one, and another one, and another one, and another one. This is a whole cluster of galaxies. This is called the Virgo cluster, since it's observed in the constellation of Virgo. I want to zoom in farther on this particular galaxy. Yes?
What is SDSS?
SDSS stands for the Sloan Digital Sky Survey. And that's where this image came from. It really came from Google Sky, but Google Sky stole it from the Sloan Digital Sky Survey. So they rightly give credit to them. Okay. Good, 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 good. And that was taken in 2007. If we zoom in on that one galaxy, it's remarkably uninteresting. It looks like just this white blob. If you have really, really good eyes, you might be able to see sort of a dark lane right here. Possibly. Your eyes have to be better than mine to see it. This is what sort of a ground-based telescope sees when it looks at this galaxy, which goes by the ever uninteresting name of M8. It's really a catalog. On the other hand, Hubble Space Telescope looked at this in the mid-90s. This was done in 1997. The nucleus of that galaxy, of M84, according to Hubble, when Hubble looked at it, looked like this. So you see all the light that's coming from the stars, this sort of black and white image. But you also see these dark lanes, and these dark lanes are dust that get in the way. They obscure our vision, our view of things. But in addition to doing fantastic imaging work, Hubble also does spectroscopy. which is to say it can take the light at any point there, and it can disperse the light into its individual colors, like a rainbow. And we can examine that rainbow and learn things. Phil has an exam tomorrow. Okay, so Hubble, one of the instruments on Hubble, which is the Space Telescope Imaging Spectrograph, STIS, put a slit in this image right here and looked at the light that's just coming through that slit. At every location along that slit, it dispersed the light, and it saw light that happens at one specific wavelength. And by looking at that specific wavelength of light, what STIS saw was that that one specific wavelength was doing this as it proceeded down the slit in terms of what wavelength do we actually observe this at. So this is a particular line that's emitted by ionized nitrogen. Under normal circumstances, all that light should be along this orange line. But we don't see that. This is what we observe. It does this very strange zigzag pattern. The zigzag pattern is a result of a Doppler shift. The gas on the top half of the slit is gas that's been shifted toward bluer wavelengths. So the color coding here is actually how blue is it. The light on the bottom half of the slit has been shifted to longer wavelengths. This is a result of a Doppler shift. So if we go back to the analogy of a police siren, when the police car is coming toward you, you hear a higher pitch, and when it's moving away from you, you hear a lower pitch. So over here, this light has a higher pitch because that material on the top half of the slit is coming toward us. The material on the bottom half of the slit has a lower pitch. That material is going away from us. So stuff on the top coming toward, stuff on the bottom going away. This is stuff that's in orbit around the center. If I can do the dance. Not very good. It's in orbit around something that's in the center of this. The interesting thing here is that the closer one gets to the center of the slit, to whatever object that is, the larger the Doppler shift, which indicates a larger velocity. We can combine that velocity with the distance that you can get by measuring the distance on the slit to figure out a mass for that object. Whatever the object that is, that gas is orbiting, we can get an estimate for the mass of that object. The mass of that object is about 10 to the 8 to 10 to the 9, 100 million to a billion times the mass of our sun. And the scale of that image, from the scale of that image, we know that that object must be less than about twice the typical distance between the stars. So this really is a single object. Yes?
I'm just curious, that image that you showed with the slit from the Hubble, is that?
Yeah.
Is there any other telescope besides Hubble that provides the sort of data that this is all based on?
So people have done this with the Keck telescope as well.
Okay.
Yeah, in Hawaii. That's sort of the other one that's sort of comparable. Keck telescope is a much larger telescope than Hubble, but it is on the ground, so it just has to deal with sort of the shimmering of our atmosphere, which sort of leads us to images like this versus images like this, which interferes, but we're starting to be able to do it. And so, since the mid-90s, let me not do that one yet. since the mid-90s, we've been able to do this. And it's sort of really the tandem between the very largest telescopes on the ground and Hubble in space that's letting us do this.
You know, on the internet you can pick up the Hubble photographs that they've made over the years, and some gorgeous, gorgeous pictures.
Fantastic. Yeah. This is not even the best image from Hubble.
No.
Okay. I mean, but even that is pretty explicit compared to that. Absolutely. I completely agree.
Rajib, could you explain just quickly a little bit more your bottom statement about distance?
Okay, so let me go back to this. So our ability to measure the distance is sort of limited by how big a pixel is on this image. Okay. So the size of that pixel translated to how far M84 is, that gives us sort of a typical distance, below which we can't really resolve. It could be less than that, but we know it's not more than that given the spacing of pixels.
Okay.
Is that more clear? And
I guess maybe because I'm thinking of this incorrectly due to having astronomy years ago, thinking of distance as far as being in distance of light years.
Right.
Speed of light. And
right.
So just two quick questions. To measure like the closest black hole to us, do you measure the light that's around the black hole to figure out its distance?
And that's exactly what's going on in this case.
Yeah.
Yeah.
And then the black hole itself, that statement says it's like equal to twice.
So the statement, the conclusion, the most robust statement that we can make based on this is that there is something that has a mass that's 100 million to a billion times the mass of our sun.
Yeah.
And the volume of space that it takes is less than about the typical distance between the stars, which is a large amount of space.
Exactly.
Okay. But put together, that indicates most likely a black hole.
Okay.
If this theoretical massive object that's maybe a billion times the mass of the sun weren't a black hole,
the mass is something that we can infer pretty well.
Right. So
based on this
how compact would it be if it weren't a black hole, so to speak? Right. If it were, I mean.
Well, the most rarefied that it could be was, say, take the distance between, say, here and the nearest star, which is Proxima Centauri. That's about 4 light years.
But I'm saying if it weren't a black hole, clearly it sort of has
What
to
else
be a
could
black
it be?
hole, right?
What else could it be?
But if we were to, so to speak,
say,
overinflate the sun, right? If we were to inflate the sun, to make it that big, that massive, what would
so if you took the sun
diameter
and
roughly
you started adding more mass, keep adding more mass,
and somehow stop it from becoming a black hole? But
but this is the question: how do you stop it from becoming a black hole? Because then we run into, let me back up all the way to here, which is if you keep adding mass to the sun, you get things that are up here. Ultimately, something like this, which is a couple 100 times the mass of the sun, it'll die out very quickly and become a black hole.
I guess I just want to know how compact is. I mean, that's clearly compact, but I mean, there's no real reference point. In the case of the regular black holes, we had the reference point of the sun and its mass and, Michigan or something like that, and then we could sort of get a rough idea of the compactness.
Right.
But how do you get an idea of this is compact, but...
So, for something that's 100 million times the mass of the sun, the event horizon of that object would be a couple times the distance between the Earth and the sun. So take the orbit of the sun, the event horizon would fill that. Okay. Now, this compactness is, at least the limit of that is much bigger than the event horizon. But we start running into questions about how likely is it if we have a different object. one of the ideas that was tossed around when these measurements came out was maybe we have a really sort of a dense cluster of very dim stars. So maybe we have a whole bunch of, go back. Ugh. Maybe we have a whole bunch of these guys. These are very cool. They don't emit a whole lot of light. Maybe we just have, you know, a billion of those in this small region of space. Well, the question, well, people could look at, well, what is the likelihood that that ensemble would survive without actually just merging together to form a single big object? Highly unlikely. So those kinds of models have been sort of ruled out based on other theoretical.
Out of the billions of galaxies out there, what percentage of them have black holes? All of them do?
All.
Now, is it, when we say all, does that mean they just have one at the center? I see. Is that what sort of keeps the thing moving?
Nope. This is another part of the conundrum,
No.
which is the sphere of influence of the black hole is much smaller than the size scale of the entire galaxy.
Oh, yeah.
And yet, we observe a relationship between the two.
Mm-hmm.
And the question, one of the leading questions, driving questions is, what is driving that relationship? Absolutely. Let's go back to this. There's actually a black hole that's closer than M84, and that's the one that's at the center of our own galaxy. So, in the infrared, we can peer through all the dust in our own galaxy and look at the center of our own galaxy. And this is work that's been done by Andrea Ghez at UCLA. She's been observing the center of the galaxy since about 1995. And specifically, she's been looking at stars at the center of her own galaxy. And she's put together sort of this montage of images where she can take a given star like that one, and she's been able to trace that it is orbiting something that's right there. Moreover, these other stars are doing that also. There is something right there that all these stars are in orbit around. She's been doing this for the past decade and a half, and she's put together a very nice movie. The last image here, you'll see it's 2010.3, which is approximately March of last year. With these orbits, she can figure out what the mass of that object is. The mass of that object is a few million times the mass of the sun. Now, we don't actually see a star there. If there was a star there, it would have shown up in these images. If there was, say, just a very faint object, she could add all the images together and she would have seen it. It's not something there. There's something very dark there that doesn't emit any light whatsoever. It's very compact, a few million times the mass of the sun. It's definitely much smaller, much smaller than the orbits of these stars.
Question. They say the fastest thing known is the speed of light, but isn't
Yes.
the gravitational pull of a black hole faster than the speed of light if it's sucking the light?
Well, I guess I don't understand, because gravitational pull is not something that we can couch in terms of a velocity. So I guess I don't understand the question.
Maybe it doesn't make sense.
So we can talk about the escape velocity.
Were you here when he talked about the escape velocity?
No, I wasn't here.
Okay,
yeah,
so-
he covered it at the beginning.
Yeah, so some of these stars, they're far away enough from the black hole that the escape velocity is less than the speed of light. It's only when you get down really into the core that the escape velocity from the object exceeds the speed of light. And that's sort of the region where you see as being black.
So the mass, as I'm hearing you say, of the black hole is actually stronger than the ability of the light to escape. And it really is being pulled in. The light is being pulled in.
Yeah. Right.
So it doesn't exceed the speed of light then if it's actually pulling the light? That's what I just don't understand.
Well, this goes into, well, how do you pull on something that has no mass? And this gets into sort of what Einstein was talking about in terms of his view of what gravity was. And so his view was that gravity was this distortion of the actual fabric of space. And so light, once it falls into this region where space itself has been so distorted, no matter how fast it goes, it can't escape that region. So it's really a question of escape velocity.
Okay, I always thought of the black holes as a vacuum.
Nope, not a vacuum at all.
It's not a vacuum?
Nope, not at all.
Once a star is pulled in,
Sure.
does it add to the mass of the black star?
If it actually gets pulled in, it will add to the mass, yes.
Now, you know that we've noticed that there are these, I don't know, shafts of light, you know, that are escaping from the black hole.
Yeah, these
Now,
jets.
Sometimes called tunnels or whatever. I just wonder, what's happening to the mass that's being added to the black hole and the light that was there?
So the mass that gets added to the black hole,
Mm-hmm.
the black hole gets more massive, and it's just part of that object, whatever was in the center. The light, so the stuff around it, before it falls in, it can emit light, and that's part of what we're seeing, say, with M84. Once the material falls in, it can no longer emit light, because the escape velocity is larger than the speed of light. And so there's that small region where we can't, inside the event horizon, we can't see. We have no information.
No.
It's only stuff that's outside that we get information. All right. So, just to summarize, yes, this answers your question. Since the mid-90s, we've been searching for black holes in the centers of galaxies, and every single galaxy that we look at, we see a really supermassive, I have to call them supermassive black holes, because they have masses in the range of 1 million to 1 billion times the mass of the sun. That's what this number means. 10 to the 6 to 10 to the 9. That's the symbol for the mass of the sun. And some of the curious things that we're finding is that that mass is proportional to the velocity dispersion of stars that are well beyond the sphere of influence of the black hole itself. Right? So in this case, I showed you stars that were in the sphere of influence at the heart of our own galaxy. But us way out here, the sun, the black hole has no effect on us, really. We're well beyond the sphere of influences.
You said all galaxies have a black hole, assuming at the center.
Yeah.
Which came first in the evolution of the universe? Do you know if the
This
black
is
hole
a
came
fantastic
before?
question, and it's one of the driving questions that we are trying to understand.
Okay.
How did those evolve together?
Yeah.
Did
well,
they evolve together, or did one come first?
That's what I was asking, the chicken or the egg.
Yeah.
How many stars came
Yeah.
early in the
We-
process?
Yeah, we have that chicken and egg problem. That's one of the leading questions. So I don't have an answer for you. If I did, then there wouldn't be a point to doing the research. I might have a Nobel Prize in this point. Which would be great for tenure.
It'd be great for you on Flint, too.
Also, that mass is also proportional to the size of the bulge. And that's a specific part of the galaxy that's also larger than the sphere of influence. You can just think of it as being the mass of the galaxy itself. So there's a relationship between the mass of the black hole itself and the mass of this larger thing that hosts the black hole. And a priori, there wasn't really a reason why those should be related. This was actually work that was done down in Ann Arbor in the middle of the last decade. So, some of the driving questions that we had is, which came first, or did one come first, or did they both happen together? And how do we get these really massive black holes if we can't just spontaneously form them from, say, a supernova? Well, they have to be grown. We have to form smaller ones maybe, and maybe the smaller ones merge together and form bigger ones. Another way is maybe through a sort of a slower mode where stuff is just gently falling in, and over the course of time, mass builds up and the black hole gets larger and larger. That's an idea. I want to show you a simulation. I hope this works.
To give some idea about the density, you know, what would a, let's say in a black hole, what would a grain of sand weigh?
What would a grain of sand weigh?
Or something the size that we know?
Well, so like the escape velocity or weight also depends on how far you are.
Okay.
So the astronauts up in the space station, they feel less gravity, so they weigh less than we do here on Earth. So I guess it depends on how close you want to get to the black hole. I mean, if you're standing on the surface, oh, I've never actually done that question, that calculation. I don't know if you have.
I know the neutron star one, and that's like a teaspoon about a ton.
Okay, yeah,
it's
so
heavier than that.
yeah, so it's definitely much more massive than that. So a neutron star, which is this cylinder that's held up just by the same kind of pressure as this, essentially. If you take just a teaspoon of that, it weighs about a ton. These things are much, much smaller, more compact.
Okay. So the density of within a black hole would be far heavier.
So the density inside a black hole must be
Infinite?
infinite, because it has mass, and the object inside takes up 0 volume.
Mm-hmm.
So that becomes an infinite density.
It's hard to grasp.
It is. Infinities are always hard to grasp. I told you. All right, let's see if I can run this simulation. Because this is a simulation that's been done by a few colleagues. And what's showing is a story of what happens when two galaxies collide. So at the centers of these two galaxies, the cool thing with this simulation that it is, it's actually stuck in a black hole at in the centers of each of those galaxies. And the matter they treat as a fluid, and they also have dark matter, which they just have as particles, and all they do is react to gravity. That's all they do. Now, in this simulation, we have these two things that they sort of spur together. I'll play the simulation again also. The color coding here talks about how hot that material is. And you see there's lots of stuff happening, so I'll go through this again. It got very red. It got very, very hot. That gas got very hot. What's left in the end is these two black holes, and they're going to merge together to form a single larger black hole. At the same time, there was lots of other stuff happening. Let's go back and look at that again. Let me try and do this. Let's go back. Do this again. It plays again. So here's these two galaxies. They're going to merge together. As they're falling toward each other, they're warming up. You see the colors changing. There's going to be a shock right in the middle where it gets really, really hot. Gas is being driven into the centers of those galaxies, so they're going to be falling into the black holes. Also, at the same time, some of that gas is going to be forming stars. So the gas gets compressed, the gas gets heated up, fusion starts happening, so we have stars. In this story, something else happens. that's happening right now, which is that gas is being blown away from the black holes by some mechanism. And it's going to happen again once we sort of have a coalescence of those black holes. See it about now. So a whole bunch of gas just got blown out from the center. This is an interesting story that's told by this computer simulation. And all they did with the simulation was they just programmed in physics that they thought was relevant. And they let the computer tell them the story. Well, this, I'm going to go over here. They took little snapshots. They put together sort of a montage, telling a story of what happens when you take two normal galaxies and then you let them collide just from gravity, just because of gravity. We can take this story and we can actually test this. We can actually go and look. Do we see things that are like this? This is a bit of anthropology done on the scale of galaxies. So we see different stages in the evolution of, say, a particular galaxy, that one at the end, and asking, how did that thing form? Where did it come from? Maybe what I glossed over here, let me go back, is that understanding how these black holes formed, since there are connections between the masses of those things and the galaxies that host them, understanding how those grow is also trying to understand, how do galaxies evolve? How do galaxies form? So this is providing another bigger context for where our work is applicable.
Just quickly, comparatively, the Milky Way is what size of a galaxy? Small, medium, large?
So the black hole at the center of the Milky Way is about 3 million times the size of the black hole.
Yeah.
It's about, statistically, and this is true for overall galaxies, it's about, I think it's like 2% of the mass of the entire galaxy.
Okay. And so the size of the Milky Way, how is that compared to other galaxies?
It's sort of rather than
Average?
Yeah, it's average. It's average.
So,
There's some that are
so the
bigger,
Milky
some
Way
that are
could have been two smaller galaxies combined?
Exactly. And in fact, we also are seeing now the Milky Way in the process of gobbling up other smaller galaxies. We actually observe that. So things like this, at least on some scale, do happen.
The M48 that we saw earlier, isn't that one of the closer galaxies?
That's
to
what
us?
it's in the Virgo cluster. Let's see, the Andromeda galaxy is the one that's closest.
Andromeda, that's
Yeah.
that's not M48 though.
No, that's not. That's actually M31 in that catalog. Yeah.
These two that you're showing in the computer demonstration look like they're spin axes in a plane.
Yes.
What would happen if they weren't? If they were...
It might be a little different, yeah.
A little different?
Yeah, yeah. And so the theorists have gone and played with various parameters. Yeah. And so exactly, the exact features, the way they get manifest, maybe it's not like this, maybe it's a little different. Yeah.
Well, there are photographs of colliding galaxies that are actually crossed from one another.
Right.
And you see two distinct disks that are perpendicular.
And there are some fantastic examples in that. So we do see we observe various stages in order to test this sort of story. And the relative numbers in which we see them, the various stages, are consistent with this story. Let me skip this in the interest of time. We're going to skip all the universe as a stage. This is another computer simulation. We're going to skip all that. Because I want to get to this. So, we saw in the simulation at least, this feature that a whole lot of gas got blown out. This is very strange. Because we want to be feeding black holes and making them bigger. We don't want the gas to escape. Or do it. So this is a spectrum of an actual black hole that's accreting. This is a very typical spectrum. That's why I'm showing it. And we're going to use this as a reference for the next 2 slides. Okay. What we see here is this very general continuum here. And on top of that, we see these lines of emission. This is sort of the visible region down here. So this is plotting flux, how much light we see, versus the wavelength of the light. So over here is ultraviolet. Over here is visible light. I'm going to continue extending this over here to even farther in the ultraviolet. And really it looks basically the same. You have this sort of general level, and on top of that you have these emission lines. Occasionally though, and by occasionally I mean probably 20% of the time, we see something that looks like this instead. So instead of this, where it's just a continuum and emission lines on top of it, these emission lines come from gas that's ionized. So this particular line is coming from carbon in that gas that's been ionized not 4 times, but 3 times. This is coming from silicon in the gas that's been ionized 3 times. This is from oxygen that's been ionized 5 times. Sometimes we also see this, where we have material here that is absorbing light. It's absorbing light, so we know it has to be between us and the object emitting the light. But it's also been Doppler shifted to the blue. So it's coming at us. This is material that's being injected by the environment of the black hole. And this could very well be a signature of that material that we saw in the simulation. And we're trying to understand some of the details of how this happens. One of the questions we want to know, well, how does growing a black hole make it skewed? Maybe I'll show this animation. And in the interest of time, we'll wrap it up. So here's sort of an artist rendition of what might be happening. So here we have a black hole at the center, this very massive black hole. Here we have this disk of material that's sort of spiraling in. And slowly it's going to fall into that black hole. As it falls in, it's getting hotter. And so the color of that material is changing. That's what these colors are denoting. But also, in this artist's rendition, you see this stuff that's being spewed out from those regions. It's not coming out of the black hole. It's coming out from this material. So the stuff on the surface of that disk is what's being driven away by subatoms. Here's sort of another computer simulation that's done by another colleague of mine. I tried to put this on sort of the same scale as that image in the background, where the black hole is there. This is sort of a cross-section of that disk of accreting material. And he put some shape to it, like this. This is all material that's being driven away. In this simulation, the thing that's driving it away is light. This stuff down here, it's getting very hot, and so it's getting very, very bright. That light from the extreme high temperatures is driving this gas away. Now the question is, do we see this? At some level, we do. Let me skip all the messy equations. One thing we expect to see is that the more light we have, the faster we can drive away material. Here's a plot where I'm showing how fast is the material going? I can measure that using the Doppler shift. Versus how bright are these objects that we see? These are creating supermassive black holes. And in some sense, we see this envelope. We see lots of objects over here, no objects over here whatsoever. So there does seem to be some sort of correspondence with, in order to have large velocities, you have to have brighter objects. So we're getting into some of the details and trying to understand the processes that inform, let me go back, simulations like this, and even on a grander scale, simulations like this one. Let me go back a ways there. And in so doing, we're also shedding some light, as it were, on some of these other processes, like how the galaxies form.
What hypotheses are you testing?
Hypotheses? Mm-hmm. So, one hypothesis is that this, go back to the simulation over here, that this is being driven off by light. That it's actually what we call radiation pressure. Mm-hmm. It's pressure from light that's actually driving these. Does it actually work?
So in essence, you've got light being sucked in, but at the same time,
light doesn't get sucked
being released.
The light out here, it's free to go off because it's not inside the event horizon. Mm-hmm. Okay.
So it hasn't reached the event horizon?
No, this is stuff that's well outside the event horizon.
I see.
Yes. Terry, I think probably exhausted our time, but definitely questions.
Yes, are there any final questions?
Yeah.
A couple should be super quick. So I just want to sort of confirm. So it seems like the main going theory, at least in the way it came across, was the collision of the galaxies. Is that's going to be the main
right, and that might be what's driving some of these
things. The supermassive black hole.
Right.
Okay. Two, this is really just a technical.
Sean is going to be telling another part of that story on Friday.
Cool.
At the Super Research Conference.
This just sort of technical thing. That one animation you had of the Milky Way center, with the stars going around the galaxy in the middle of R.
Yep. And that's actually observations. That's not.
Yeah.
That's not. A
I'm just assuming you could get the right answer for the mass of that body using Newtonian mechanics.
Exactly. That's how it's done.
Right.
That is exactly how it's done. And so that's how we get a few million times the mass of the sun.
Okay. Yeah. And then the last thing is that you mentioned that in that simulation of the